most conducive environment for jazz. I mean, it's really not. In fact, it's terrible. It's really noisy. It's very narrow. It kind of feels like a coffin. You have to lie down. You can't move. It's 130 decibels of background noise. You have to take this environment and sort of say, okay, well, how do I convert this experimentally into a setup that can be ecologically valid, meaning that when a musician shows up to actually do an experiment, that they're not going to think to themselves, what was that? That had nothing to do with what I normally do. And that's the thing that has bothered me a lot with a lot of the neuroscience of music, is that a lot of times when I'm reading a paper in the neuroscience of music, I can't even tell that it's about music. And so I was really worried about the jazz experiments, that that's what would happen, that somehow the jazz musician would say, like, yeah, that was kind of interesting, but I got to say, I don't think that reflected what I do at all. And so fMRI rests on this principle called bold imaging, so blood oxygen level dependent imaging. It's a pretty remarkable finding, which was discovered in the early 90s, which is that oxygenated blood and deoxygenated blood have different magnetic signals. And so an MRI machine can detect signal changes in ratio changes for oxy-deoxyhemoglobin. That means that when a neuron in your brain is active, it's getting more blood. When it's getting more blood, that blood flow is consuming oxygen. There's a change, a relative change in the ratio of oxy-deoxyhemoglobin, which leads to detectable signal increase. That signal increase is the bold signal, and that's what we're measuring in fMRI. Now that implies a few things. First thing that implies is that this is a vascular method. Okay? So fMRI is not an electrical method. It doesn't have the precision of neurons. It's not like an EKG of your brain. An EEG is like that. Okay? fMRI is a hemodynamic method that's very slow. It captures impressive amounts of changes in blood flow, but they happen over time. And there's this lag that's called a hemodynamic response that takes place that you have to account for in any fMRI experiment. That sort of implies that if you want to look at how John Coltrane hit that 1B flat over this G minor chord, this is not the best modality to do it. Okay? The other thing is that when you look at fMRI data, it's not usually pretty anatomic pictures like you're seeing here on the left with the superior temporal gyrus is just highlighted for you. In fact, it's a statistical cluster. Okay, and I'm using the word cluster liberally here. There's really just a broad patch of activity from which we infer a maximum of activity. And this really occurs throughout the brain. And we're trying to say, okay, based on that, I'm inferring stereotactically that took place in the superior temporal plane. And so there's lots of imprecisions, even in terms of the anatomy of these things, much less the temporal resolution rates. So there are reasons to avoid fMRI, and they are the following: physiological, experimental, and then also instrumental. And again, I don't want to belabor the point here, but just suffice to say that for those of you that want to study music using fMRI, just realize that you can't just go in there with a tuba and just start playing whatever you want to play. It just doesn't work that way. And so at the NIH, I spent a couple of years to try to get a piano that we could use for fMRI experiments. This is a video showing you how that works. So this is a plastic MIDI piano keyboard that we use for the jazz experiments, and it's a 35-key keyboard that is designed to fit both inside the scanner, be magnetically safe, have minimal interference that would contribute to any artifact, and have this cushion that it can rest on the player's legs while they're lying down in the scanner, laying on their back. And it works like this. This doesn't actually produce any sound. It sends out what's called a MIDI signal, or a musical instrument digital interface, through these wires into the box of the computer, which then trigger high-quality piano samples like this. Now I'm going to demo it for you. This is a double mirror. That piano, it took me actually 2 years to get to work. And I remember after it was actually done, when it actually was working, I was like, wow, it's working. It's like, now what are we going to do? We have to have an experiment to use this with. And so the whole experiment designed around the fact that in jazz there is a memorized component and an improvised component, and that the chord structures are typically the same. And so we brought jazz musicians to the NIH and had them memorize a novel blues that we wrote for them. They memorized this piece, and then they would be presented with the same backing tracks, and they would either play the melody or improvise on the melody using the chord structure as the basis of their improvisation. And so the kind of paradigm was sort of like this. There was a simple paradigm called scale, which was a way to control things scientifically really well because they were playing one note per beat. It was all within a confined range. It was just one octave right hand only. And so from a scientific perspective, this is a much better experiment. But it's really pretty boring because what you're listening to is somebody either playing a C major scale up and down, or improvising on a C major scale. I didn't want to just do that, even though that's actually a pretty suitable experiment. So what we did was have them memorize this piece here on the lower left. And this is called magnetism. And this is a 12-bar blues. And you can actually see the chord changes there. And you're going to hear an improvised solo that was done by one of the great jazz musicians that was in the study here. This was recorded in the scanner. Again, you can tell they're really playing in there. Okay? I'm not going to say that it's the world's best jazz. It's not. It's a 35 plastic piano keyboard. They're on their backs in an fMRI machine. It's limited. Okay? On the other hand, these musicians are so talented that I often didn't start the scanning because they were warming up and it sounded so amazing. I said, wow, listen to them play. Let's just let them play for a bit. And so these musicians were really game, and they really got into the experiment because they all often wanted to know this question for a long time. What am I doing when I'm actually improvising? And so I use something called statistical parametric mapping. It's probably one of the most common used fMRI software packages in the world. It's very non-transparent to me, very kind of frustrating at times, but enables me to do some pretty simple computations and to apply something called the general linear model to look at statistical voxels of interest. And you take a voxel by voxel comparison after you correct the images for movement and smoothing. And so with our first experiments, this is sort of the one of the messy brain maps we have. And I'm going to draw your attention to the prefrontal cortex here. And there's two key findings that are probably better shown in a 3D rendering later. First thing is that when musicians went from memorize to improvise, this broad patch of dorsolateral prefrontal cortex was relatively deactivated. In the meantime, this focal patch of medial prefrontal activity was noted, sort of dissociation in prefrontal cortex. We thought that this was pretty interesting because you don't normally see a dissociated state of activity in one task in the prefrontal cortex. And so it's worth sort of looking into what these things do. Now, the medial prefrontal cortex is a very interesting area of the brain because it's sort of an autobiographical, self-referential part of the brain. It's part of what we call the default network, which is that when you're not doing anything, what is your brain doing? Well, when you're not doing something, your brain is actually very active, and the part of the brain that's active is along this midline, which is called the default network. Well, it turns out that in music, if you hear a song that evokes an autobiographical memory, say, oh yeah, I remember hearing that song in 5th grade, the medial prefrontal cortex is active. If you tell a story about yourself, this part of the brain is active. And when you're doing a jazz solo, this part of the brain is active. That's interesting because in jazz, a lot of musicians consider their improvised pieces to be kind of musical signatures of a sort. You can kind of identify a musician right away by their improvisation without knowing who it is playing. And so there's an identity that's linked to somebody's output that's part of what makes it a very personal thing. In the meanwhile, there's this broad shutdown of lateral prefrontal regions. And again, these are multifunctional areas of the brain. They're not the jazz areas of the brain. Okay? These are not. It's not just that you lost this area of the brain, you just couldn't jam. Okay? If you lost these areas of the brain, there's many, many functions that would be devastated. However, some of the important functions of these things are to consciously monitor your output and to inhibit yourself to make sure that what you're doing is correct and appropriate. It's also involved in effortful planning in certain tasks. And so what we're having is a shutdown in a lot of these processes that normally provide a sense of control over our output in favor, we think, of generating new activity that's not so restrained. And you don't want to have such tight control from an executive perspective over these prefrontal operations when you're trying to come up with something new. And so we found that this kind of dissociation of prefrontal cortex activity was kind of an intriguing way to think about jazz. Like, maybe we're onto something here. Maybe the prefrontal cortex has a lot to do with how a musician or any artist is able to be creative and generate something new. Because this part of the brain is allowing you to get rid of some of your self-monitoring impulses, and this part of the brain is allowing you to self-express. Now again, this is, and part of the problem with fMRI is it's always very interpretive. Right? There's no law that says that has to be why these areas of the brain are doing that. But it's an interpretation that makes some sense, and we'll see whether or not it bears out in future experiments. Now, after I did that experiment, we sort of said, well, okay, how do we summarize this? Well, let's summarize this by saying that in jazz, solo improvisation in this kind of flow state is a goal-directed behavior that occurs in the absence of the context that's normally provided by these lateral prefrontal regions that leads to what we call a defocused form of attention. And maybe this defocused kind of attention will lead to sudden insights and sort of unplanned associations. And maybe that's part of why creativity is, and the jazz is, the sound of surprise, because you never know what's coming next. Okay? Now, when I did that experiment, I had a lot of questions in mind right away about, first of all, why that experiment was limited, but also what I really wanted to get at, which is this idea of music as being meaningful, and how it is that musicians can communicate with one another, and have that communication be something that is effective even though it's wordless. And so in jazz, there's a convention that's called trading fours, which is when two musicians or more musicians will take turns, a call and answer kind of thing. You play 4 bars, I play 4 bars, and we're going to respond and interact with one another. And this is a video of Herbie Hancock's band, Trading Fours. So hopefully you can see that they're talking musically. Okay? They're not using any words, and it's not clear what they're saying, but they're communicating something. And that communication is profound for each of them, and for the listener, it's also something that is substantial, even though the nature of that substance is hard to define. And that is what's odd about music compared to language. Language has words that are very specific, and those words are used to convey a very precise meaning. Nobody can tell you what music means. Okay? Let's do a little experiment here. Da-da-da-da. Okay? What does that mean? It means 1,000 things, 1,000,000 things. It means whatever it means to you. Okay? And one person's definition is no more correct or incorrect than your own. Beethoven's definition is no more correct. He might have had an intention when he composed that. That wasn't Beethoven, you can tell by my singing. He might have had an intention, but that intention is diffused through music, through the use of notes. It's not the same as language. And so, to try to capture this in an experiment, I wanted to bring now not just one musician, but 2 musicians into the fMRI scanner. And I wanted them to interact with one another. One musician would be scanned while another musician is playing back and forth with them. And so this time we brought, again, musicians to Johns Hopkins, and we had them memorize a 12-bar blues, Dorian blues, and we had them take turns, okay, 4-bar segments. Everything they did was in 4-bar chunks here. So even when they were memorizing things, they were memorizing in 4-bar chunks. And this is the piece that they played. And so the turn taking kind of goes like this. It's marked there in red and blue and red. So this is the piece.
Play melody.
So musicians in here. Musicians do this over and over again, and the setup was actually, it takes a lot, for me, it takes a lot to make these experiments actually work and not feel too cumbersome, because there's a lot of stuff going on in the background, but in the end, I just want the musicians to feel like they're just